Right. Let's now begin part 3 of the chemical bonding series. And what we're going to do is take a look at what's called bond characteristics. It means different bonds have certain properties. And because they do, the molecule itself, once built, sometimes has a polarity to it. And those two things we're going to look at now. The critical idea in this idea of characteristics of bonds is the concept of electronegativity. Electronegativity, as it shows, is the ability of an atom to attract to itself electrons. And different atoms can do this to different degrees of ability. And what has happened is chemists have built a chart, and the chart reflects this level of electronegativity, the ability to attract electrons to themselves. And when they built this, the fluorine has the highest electronegativity relative to all the other atoms. It's drawing electrons to itself better than any. Now, the illustration below is kind of a fun diagram. What it shows is, it attempts to show that on the right, perhaps this is fluorine, it is drawing electrons to itself better than the ability on the left. And there's an asymmetrical pulling of the electrons towards it. Now, this here is a chart of those electronegativities. You'll notice that fluorine is the highest, it's on the right, and it has a value of 4. Now, there are no units assigned to electronegativity. It's just a degree of pull that can be exerted. And take a look, lithium, for example, has a value of 1. And what happens is when, for example, fluorine is bonded to lithium, what we do is compare the difference in electronegativity. And what happens is if that difference, you can see from the chart above, if the difference between the two atoms is greater than 2, then the bond that forms is going to be an ionic bond. If the difference between the two atoms that are connected, if the difference is between 1.0 and 2.0, then we can consider it very, very polar, and meaning that the electrons are pulled heavily to one side of the molecule. It favors the side that has the greater electronegativity. If we go back to this slide, it's nicely showing this. The fluorine, for example, has a very large bulge around it, and it's reddish. And what that symbolically is saying is the electron cloud tends to hang out around the fluorine side, while the other side, perhaps that's hydrogen, it's not as good at attracting electrons, and therefore there's less electron time spent there. Now, it's very important to keep straight. This molecule is not an ion. It doesn't have an extra electron or is missing a full electron. Instead, electronegativity, as shown by this chart, represents a unequal distribution of those electrons for that bond. And these values apply to just the one bond between the two atoms. Now, the result of all of this is we call the bond polar. And the word polar simply says that the electron density, or the concentration of the electron cloud, is not equal between the two atoms that are bonded together. And because that is true, one end of the bond is going to be positive, meaning it doesn't have as much electron cloud around it. And of course, the other one would be negative because there's a greater density of the electron cloud there. And when you have a polar covalent bond, we call that arrangement a dipole situation. So polar covalent bond, also called a polar bond, is a covalent bond with greater electron density around it than another. And we see here that fluorine, which has a bond to the hydrogen around it, we can represent it diagrammatically, which we've talked about already, in this manner. And we have a region that's electron rich and a region that's electron poor. and we can match that against the Lewis dot structure. And it should be noted that fluorine has 2, 4, 6 electrons around it which are not part of the bond. It's very important to understand that those electrons are not part of the electron-rich, electron-poor regions because they're not involved with the bond. We discuss this idea of polarity only in terms of where the bond exists, and the other electrons not involved are not contributing to this polar property. Now, to denote an area that's electron rich, we refer to it as polar negative and polar positive. And that unusual sign you're looking at there is representing simply the idea that it's a polar arrangement. Written in a more formal way, we would write it as shown at the very bottom there. So these are polar covalent bonds or polar bonds. Now, we then want to indicate the direction of the dipole. And all we're indicating there is the idea that we have a plus region and a minus region. And the drawing that you see is how you would represent that dipole in terms of direction. Again and again, these descriptions apply to only the particular bond being looked at. And the fact that an atom may have other bonds going on is not relevant because it's just this single bond that we're studying. Now, the bond characteristic, as you might start to suspect, there's a gradation, meaning that the degree in which there's a difference in electron density, the degree to which there's a difference in electronegativity between two atoms can have a variety of values. You can have an electronegativity difference of 0, in which case the electron cloud is distributed equally between the two atoms bonded, all the way to a very great electronegativity difference. And because there are these different levels of electronegativity, you get different bond types. When there is 0 difference or very little difference between the two atoms' electronegativity, the bond that forms is called a covalent bond. However, when there starts to be an intermediate level of difference between the two atoms in electronegativity, that bond now does not have an equal distribution of the cloud, and so we call it a polar covalent bond. Finally, if electronegativity difference is very large, as an example, lithium bonded to fluorine, that difference is 3. That's a very large difference, and the result is a full ionic bond. And so the covalent characteristic, meaning the sharing of the electrons, gets less and less as the electronegativity gets greater and greater. And of course, the ionic characteristic increases that way. So we can now talk about bond polarity. Let's begin on the right. When you look on the right, you'll see it's chlorine to chlorine. The difference between chlorine and chlorine is 0. Therefore, the bond is considered completely nonpolar. When you look at the bond between hydrogen and chlorine, let's look up that value. So we're going to look up hydrogen and chlorine. I'm back through this now. Bear with me. We're looking for a hydrogen and chlorine. I don't have it on. There we go. Take a look at hydrogen. Hydrogen has electronegativity of 2.1. Chlorine has an electronegativity of 3. So there is a difference. There's a difference in electronegativity strength of 0.9. So clearly, at a difference of 0.9, you are not going to have a true covalent because there is a difference between the two. And so we would call HCl polar covalent because there's a difference of 0.9. Now if you look at sodium chloride, the sodium chloride electronegativity difference is greater than 2. And because it's greater than 2, that kind of bond is considered an ionic bond. So let's try to classify the following bonds as ionic, polar, covalent, covalent. So here's an example. Let's bond together cesium chloride. Well, cesium's electronegativity, if you look on the chart, is a 0.7. Chlorine electronegativity is 3. So the difference is 2.3 between those two. And because it's beyond 2, that bond is called an ionic bond. Now what about H2 hydrogen sulfide? Hydrogen is at 2.1, sulfide is 2.5. So the difference is 0.4. That bond is going to be polar covalent. Now again and again I will say to you that a difference of 0.4 applies only to the bond between one hydrogen and one sulfur. The fact that there are two hydrogens does not affect the value. And finally, the nitrogen bonded to nitrogen, it's into gas. You have a difference of 0, and therefore that bond is going to be a covalent bond completely. And so we're looking to categorize the kind of bonding that takes place, and that's based upon electronegativity differences. Now what's a dipole moment? We've seen this drawing before, and it shows us that hydrogen fluoride, hydrogen is a polar plus, fluoride is a polar minus. We draw the dipole as a vector or an arrow in the direction of the negative region, and we show it again as a space filling model as you see here. So the dipole is the amount of pull of electrons towards one side of the bond. The dipole moment is the measure of that value. And so dipole is simply a term used to represent the strength of that difference. Now vectors simply means that there's a direction to the charge or to the polarity. So dipole moments, we see it drawn there. We have a permanent dipole here, meaning that the electrons are permanently hanging out around one region of that molecule due to electronegativity. Now this is a pretty slick diagram. Watch how this sets up. We have hydrogen fluoride. Hydrogen fluoride is polar. When we put the hydrogen fluoride in a charged field, take a look. On the left, we've got a arrangement of the hydrogen fluoride being everywhere. But when we put it in the plates, notice how everything lines up. What I mean by that is that you have all the polar positive regions facing the negative plate and all the polar negative regions facing the positive plate. Therefore, the HF molecule aligns. Now let's take a look at this in action. So we once again have hydrogen fluoride molecules. They are polar, and they're all floating around in random direction. Let's put now those negative plates and positive plates, and now you get an alignment. So polar molecules orient themselves in a magnetic or electrostatic field. So when we have these dipoles, they do not necessarily cancel each other out. When we have multiple atoms involved in the bond, you focus in on just one bond at a time. So it's possible for a molecule to have a region of nonpolar and another region of polar. So if we have differences between the different polarities of the molecule, you have what's referred to as an asymmetrical geometry. Now, what exactly does that mean? Well, here we've got a nonpolar molecule with polar bonds. Now, chlorine is more electrical negative than Be. What does that mean? What that means is that the chlorine atoms are going to draw the electrons away from beryllium because beryllium has a smaller electronegative charge. And you can look that up on the chart we gave you early on in this presentation. So what happens is we have polar covalent bonds, we have dipoles. So one wants to say that, oh, this is a polar molecule. But that's not true. The molecule itself is not polar, even though it has polar bonds. And the reason why is that the dipole forces cancel each other out. The vectors are moving in opposite direction and cancel. Overall result, it's a non-polar molecule. Here is another example of this. Notice that the two oxygens have a greater pull on the electron cloud of the carbon. Therefore, we have two dipole bonds. But because the geometry is in opposite direction, it's non-polar. Now what we have here is this. F and H are more electronegative than Be. So we do have two dipole bonds. However, F is more electronegative than H. It's a stronger dipole than the hydrogen. The result is the two dipole forces do not cancel themselves out completely. And therefore, the molecule is in fact polar because the strength of the fluorine is greater than the strength of the hydrogen. Now, what about BF3? Is it polar? Well, it turns out that B and the fluorine are going to form a balanced distribution of forces. Notice how the vectors are all moving away from each other, all moving away from the boron, and the result is they all cancel each other out. So these are polar bonds, but the molecule itself is non-polar. How about CCl4, carbon tetrachloride? Once again, you have chlorine has greater electronegativity than carbon, but they're all of equal strength and the geometry is symmetrical. So all of the vectors cancel each other out, and the result is you have a non-polar molecule. So notice it matters that the strengths balance out, and it matters that the geometry balances out. That in the end determines whether in fact you have a polar molecule. Now, here what we notice is that hydrogen has greater less electronegativity than the nitrogen. Therefore, the dipoles are all facing into the nitrogen. The result is they're not canceling, they're additive. The dipoles are asymmetrical. And because the bonds are not symmetrical, because the polar bonds are not symmetrical, then the overall molecule itself is polar. And the vector shown on the right is the total direction of the dipole. So when you have ammonia, ammonia is considered a polar molecule. Another example, fluorine is more electronegative than the nitrogen. So what happens is the poles do not cancel themselves out here because the angles are all pulling away but not against each other. So once again, you're looking at a polar molecule. NH3 is more polar than NF3. Excuse me, is it more? And the answer is if you add up all the resulting polarities of NH3 and you add up the resulting polarities of the fluorine, you will notice that the dipole moment is a larger number. is a larger number. So in fact, ammonia is in fact a more polar, a more strongly polar molecule than the nitrogen trifluoride is. Now water is superpolar because the oxygen is very aggressive at pulling the electrons away from hydrogen. So water is a very, very aggressive molecule, and that gives it some very unique properties. Now, what about this idea of lone pairs? Lone pairs are electrons that are not involved in any kind of bonding. But because they're not involved in bonding, they don't create a polarity to themselves. So let's take a look back here. You'll notice water, there's bonds between the oxygen and the hydrogens, but the oxygen has 2 extra pairs of electrons that are not involved in the bonding. Because they're not involved in the bonding, they do not contribute to the polarity of the molecule. So what happens is we do get some cancellation here of the polarity, but the bonds are not all equal. So the result is you get some cancellation, but the carbon to fluorine is still greater. And therefore, this molecule is considered polar. Now, when you have asymmetrical or unequal distribution of the dipole forces, that is when the molecule does become polar. So you got to pay attention to the direction of the polarity and also to the strength of the polarity to determine if in fact the molecule overall is polar. And remember that unpaired electrons do not play a role in making the molecule polar. Now, what these are going to show is because of the different polarities and because you can have multiple bonding, molecules take on certain shapes. And those shapes are linear, trigonal planar, tetrahedral, bent, pyramidal. And so the question is, what kind of shapes do these different molecules assume? And here what you see is chloromethane has a carbon in the middle, the 3 hydrogens, and the chlorine. So the result is the direction is in the up direction as a dipole moment, and therefore you get polar bond formations as an unequal sharing of the electrons.